All right, so let's get into example 3 of integration by parts. So remember in the beginning of the video when I said there are certain times where there will be kind of tricky integration problems where integration by parts can get kind of tricky. In the rest of the video, I'm going to be addressing how to deal with those kind of tricky problems. The first kind of tricky problem is integration by parts repetition, when you have to repeat integration by parts and you have to do it a second time. Sometimes when you finish the uv minus the integral of v du, sometimes the integral of v du, you'd have to integrate it again to get the final answer. I show an example of that in this example right here. So let's get into it. So we're going to be using this equation right here, which is going to be the integral of x squared times sine x dx. As you can see here, we would use integration by parts here because these are two functions that are multiplied by each other. We have x squared, which is multiplied by sine x. So if we do step 1 and we do our little chart here for the integration and the derivation, we can see visually which answer, whether it be the answer to the integral or the answer to the derivative, would have the higher degree of x. So let's check it out. So for x squared, if you take the integral, the answer is x cubed over 3, and then for the derivative of x squared is just 2x. Here, the degree of x is to the third, and here the degree of x is to the first. So the degree of x is 1 here in the derivative of x squared, but in the integral of x squared, the degree of x is to the third power. So for sine x, both of the x's is to the degree of 1, because right here it's not like it's negative cosine x squared or negative cosine x cubed, it's just negative cosine x. Same thing with this. So for these x's right here, the degree is both 1. So it's both has the equal amount of difficulty to take the integral of and to take the derivative of. So the integral of sine x dx is negative cosine x plus c, and the integral, did I say integral or derivative? Sorry. The integral of sine x dx is negative cosine x plus c, and the derivative of sine x is just cosine x plus c, the positive one. But both here, both of the degrees of x's are to the power of 1. So they both have the equal amount of difficulty, but for here, for the integral has a higher degree, and the derivative, the x has a lower degree. So this is so x squared is easier to take the derivative of. So we're going to make x squared our u, and since we have but no choice to put the other function as dv, we're going to make sine x our dv. So x squared is going to be u, and sine x is going to be dv. So x squared is going to be u, so and sine x is going to be dv. So since u is x squared, du over dx, the derivative of u, is equal to the derivative of x squared, so which is 2x. So du over dx is equal to x squared, and if we make our little fractions here, so that way we can cross multiply to get du by itself. Du over dx is equal to 2x over 1. So if we cross multiply this, we get du times 1 is equal to 2x times dx. Du times 1 equal to 2x times dx, and then du is equal to 2x dx. So for dv is sine x. So we do the integral of dv, which is the integral of sine x. And so v, we get the integral of dv, which is just v, which is equal to the integral of sine x, which is just cosine, which is negative cosine x. Do not add plus c yet, like I said. So now that we have our u and our dv, we chose those, and we found our du and we found our v, it's time to set up the equation. So the uv minus the integral of v du in this circumstance would be x squared minus negative cosine x did I say minus? I'm so sorry. X squared times negative cosine x minus the integral of negative cosine x times 2x dx. This is two functions multiplied again. The first function is negative cosine x, and the second function is 2x. So we have to integrate again. we have to repeat the same steps to answer this question. The answer to the integral is right here, but this right here is two functions multiplied by each other. So we have to do the same steps again. So right now, this side of the equation is done. We're not going to focus on this. We just need to focus on this forward. So we have to integrate this again. Integrate this again. So here, we're going to choose 2x. If you do the chart and you do like all the math from the integral and the derivative and see what's easier to take the derivative of and easier to take the integral of, it's going to be this. So u is equal to 2x, and then du over dx is equal to 2. So we're going to choose u is 2x is our u, and u is our 2x. So you take the derivative of u, which is du over dx, and that's going to be 2. Excuse me, we have to get du alone. So if you zoom in here, like you can make du over dx equal to 2 over 1. And then you cross multiply, and then du times 1 is equal to dx times 2. And then du times 1 is just du. So du is equal to 2 dx. Yeah, dx times 2 is the same thing as 2 times dx, you know. Vice versa, either or, tomato, tomato, potato, potato. dv, we have dv here. dv is equal to negative cosine x, and the integral of dv is equal to the integral of cosine x. You integrate both sides, and then the integral of dv is just b, while the integral of negative cosine x is negative sine x. So we have our v, and now we have our du. So we have our u, we have our du, we have our v, we have our dv. Now we can set up the equation and answer again. So here, our uv minus the integral of v du would be 2x times negative sine x, u 2x times v negative sine x, minus the integral of v negative sine x times du, which is 2 dx. And this we can integrate. You just take the constant out, and then you integrate negative sine x, and this negative is going to be a positive. So I just made this negative and put it a positive here, and then I just made and I took this negative out as well. So I got negative 2x sine x plus 2 times the integral of sine x dx. This right here, you can integrate and get like a single answer. It's not going to be like an answer that has two functions that are multiplied. This, you can get a single answer. And all of this right here just pertains to this part of this function. Just pertains to this part. So this right here pertains to this part. Okay, so if you just if we focus on the integral that I was talking about a couple seconds ago, that would be negative 2x times sine x plus 2 times the integral of sine x dx. And then the integral of sine x dx, that has like a final answer, a definitive answer. This is only one function. So now we can integrate this, no problem. So the answer would be to this, and like to the second part of that part of the integral that I was showing you would be negative 2x sine x plus 2 times negative cosine x plus c. And then, you know, you can kind of just rearrange this to make it look pretty. I took the negative out, and then I got negative 2x sine x minus 2 cosine x plus c. Remember, like I said, we can add plus c like when we're done with the whole thing. So for the final answer, we get this is from the left side of the equation from before. I think I can put that in like into like a little box right here, or like a little like thing on the side to show this was the left side of the equation, and then this is just what we just got as the integral of v du, since we had to do it 2 times. I'll probably put like the left side of the equation in like a picture here or something. So the final answer would be x squared times negative cosine x minus this whole shebang, negative 2x sine x minus 2 cosine x plus c. And if you kind of just distribute this negative and kind of like brush it up, simplify and make it look pretty, it would be negative x squared cosine x plus 2x sine x minus 2 cosine x plus c. All right, so that would be the final answer. And that's what it looks like when you have to repeat integration integration by parts twice. Also, here's a note for integration by parts when the integral repeats. So, the highest degree of the x variable in the integrand is the amount of times you will repeat the integration by parts. Now, let me explain what I mean. So, for example, let's take the first example we did, the integral of x cosine x dx, right? Let's take this. We only had to do this integration by parts once in this example because every single x is all raised to the power of 1. So you only did the integration by parts once. There was no repetition. You only did it once and it was done. The same thing with the second example we did, the integral of 2x plus 9 times e to the power of x dx. Both of the x's here are to the power of 1. And this can be kind of confusing with the exponential equation. So let me zoom in. For the e to the power of x, I'm not talking about it being raised to the power of x. I'm talking about x being raised to the power of 1. So for the second example, both of the x's are to the power of 1. I'm not talking about what e is raised to. I'm talking about what x is raised to. X is raised to the power of 1. It was just e to the x alone, not e to the x squared or e to the x cubed. It was just e to the x alone. So that would be e to the x to the power of 1 and 2x to the power of 1 plus 9. Both of these are to the power of 1. That's why when we did these two examples, we only did the integration by parts once because it was to the power of 1. If it was something like this, for example, if it was something like this, like for example, the first example, if it was no, this was actually the third example when we did the reiteration. The third example, the x squared times cosine x dx. Was this the third example? It was something like this. I can't remember. Well, that's not important. Let's just use this. For example, if it was x squared times cosine x dx, the integral of that, if it was that, the x squared, the x is to the power of 2 here, and the cosine of x, the x is to the power of 1 here, but here, the highest degree that the x is in this integrand is 2. So in this integral, you will do the iteration 2 times because 2 is the highest degree. In something like this, for example, the x, or something like this, the integral of x times cosine x to the 4th power dx, that here, x is to the 1st power, while cosine of x, the x and the cosine of x is to the 4th power. So for something like this, you will do the iteration 4 times, because 4 is the highest degree here. So for stuff like this, the degree tells you how many iterations you're going to do. That's why it's so important when we're choosing the uv minus v du to choose something that has the lowest power or the lowest degree, because we want to stop all those iterations. If for the first example, if we were to not choose the correct one as u and not choose the correct one as dv, we might end up as having to do it over and over and over again because we chose the wrong u and chose the wrong dv. It would have came out the same way, but it would have been so much more difficult. That's why when we're choosing our u and dv, you got to choose something that's as u that's easy to take the derivative of, and something as v that's easy to take the integral of, either or, because you want to choose something that has the least amount of degrees, because the degrees in the integral when it comes to integration by parts determines the amount of iterations you do. The highest degree is the amount of iterations you're going to do. For this one it's 2, so it will be 2 times, and for this one it's 4, it will be 4 times. So yeah. Topic we're going to talk about is what to do when the integral keeps repeating. There are times where you might come across an integral that after you do the integration by parts and the uv minus the integral of v du, after you do it the second time, it has to be integrated again, and you do the third time, it has to be integrated again and again and again. And this time around, sometimes it doesn't even have to do with the degrees or how high the degree is. Sometimes the nature of the integral is that it's just consistently repetitive and it keeps repeating and it's never ending. Now I'm going to go through the steps on what you should do if you come across a integral problem where the integral keeps repeating and it's forever never ending. Essentially, when a scenario comes about where the integral just keeps repeating and repeating and never ends, it requires you to substitute the integral and solve it kind of algebraically. So allow me to explain with an example. And this part is going to be a little confusing to describe, so I'll be sure to explain very slowly and very clearly. So let's take this integral right here, right? The integral of e to the power of negative x times sine x dx. We're going to solve that. So let's do our step one. Let's find what to use as u and find what to use as dv. We have our little chart here for the function, and then the integral and derivative of each function, and then we're going to compare the degrees of the x's for each integral and derivative for each function, and find which power is higher. So for both of these, they're both raised to the same power, and they're all raised to the power of 1. So for this and this one, they're both raised to the power of 1, so they both have the same amount of easiness to integrate it and to find the derivative. And for sine x, it's the same thing. Both of the x's are to the power of 1, so it's equally as easy to find its integral as it is its derivative. So in situations like this, when this arises, you can use either or as u or dv, because both of them have the same amount of easiness, because they have the powers of the x's are the same, so they have the same powers, and the x's have the same powers or whatever. So sorry, I feel like I'm being repetitive, but yeah, for situations like this, you can choose either or as u or as dv. But the catch is, if you do a repetition for the u and dv, you have to keep the same type of function as u and the same type of function as dv. So for example, this is e to the negative x, right? It's an exponential function. So if you do another iteration, make sure the exponential function is your u if you choose this as u the first time. And this is a trigonometric function. So if you choose this as your dv, make sure that the second time around, when you do the second iteration or repetition, if you will, of the uv minus b du, if this is your dv, make sure the trigonometric function is the dv the second time around. So just for the heck of it, I chose u as e to the power of negative x, and I chose dv as sine x. So since u is e to the negative x, the derivative of u, which is du over dx, is going to be the derivative of e to the negative x, and the derivative of e to the negative x is negative e to the negative x. So we got to get du by itself like we've been doing, so we can make the negative e to the negative x over 1. So du over dx equals to negative e negative x over 1, which also means du is, and if we cross multiply, we're going to get du times 1 is equal to negative e negative x times dx. Du times 1 is just itself. So du is equal to e to the negative x times dx. And so since we have our u, we have our v, we have our, like we said, we have our v, then we have our du. We can apply this equation now. So u, which is e to the negative x, times negative cosine x, which is our v, is equal to, not equal to, minus the integral of, minus the integral of v, which is negative cosine x, times du. And du is negative e to the negative x dx. This is another iteration of the integral, so we have to do it again. So yeah, this is the equation that we had before, the integral of negative cosine x times negative ex dx. That was what happened to be the integral of v du. So we gotta do a second iteration. So multiplying the two negatives, let me rearrange this. Multiplying the two negatives makes it positive, so I took this negative and took this negative and just made it positive, and made the whole thing positive just to, not have to deal with the negatives. So we have cosine x times e to the negative x dx. We have to integrate this, and we're going to use integration by parts because this is two functions that are multiplied by each other. Like I said before, use the same, let me get this so you can read the whole thing. Use the same u and dv format as the first time. First time around, we made the exponential function, which was the e to the negative x, in the other function, u. And we made the trigonometric function, which was the sine, dv. So let's do that again, and let's use the same format for u and dv as we did the first time. Here, this time around, we have cosine x and e negative x as our two functions that are multiplied together. We're going to make our e negative x our u. We're going to make the exponential function our u. And we're going to make our dv cosine x, because that's the trigonometric function in this case. Like this case up here, like for this one, in this case, we're going to follow the same kind of format, you know? So, u is equal to e of negative x, and then the derivative of u, which is the derivative of e to the negative x, is negative e to the negative x. So du over dx, which is the derivative of u, is equal to negative e negative x, which is the derivative of this. So we gotta get du by itself. So we're gonna put negative e negative x over 1, because anything divided by 1 is itself. Cross multiply. Du times 1, which is this, is equal to negative e negative x dx, which is this, cross multiplied. And for dv, we have dv is equal to cosine x. So the integral of dv is equal to the integral of cosine x. So v would just be equal to sine x, because the integral of cosine x is just sine x. Remember, don't put plus c yet. And so here, the integral of uv minus, not the integral, uv minus the integral of v du would be e to the negative x, that's u, times v, which is sine x, minus the integral of sine x, which is v, the integral of v, the integral of sine x, times du. And du is negative e negative x dx, which is right here, times du, which is negative e negative x dx, right? But if we just focus on this part, the integral of v du, which is this, the integral of v du, this is still two functions. Again, this function sine x and the negative e to the power of negative s is still two functions multiplied by each other. So we would have to do integration by parts again. And it's just going to keep going and keep going and keep repeating. You see what I'm saying? So for our first iteration, which was the first time we did the uv minus v du, we got minus the integral of v du, uv minus the integral of v du. For our first iteration, for the uv minus the integral of v du, we got this, which was e to the negative x times negative cosine x, that was uv, minus the integral of v du, which was the integral of negative cosine x times negative e negative x dx. That was what we got when we did it the first time around. Then we did this one, and then this is still highlighted in orange the second time around. So the second time around, for the second iteration, we got this. I just brought this down, and then I did uv minus v du to this. So when you do uv minus v du to this equation, to this integral right here, you get this. So I brought this down and then did the second iteration, and this is what we got for the uv minus v du of this. They're both in the orange box, and then this is just brought down. For the second iteration, we got e to the negative x times negative cosine x minus e to the negative x times sine x minus the integral of sine x times negative e negative x dx. This is still two equations multiplied by each other, so we would still have to do it again. But here's the interesting part. We started off with, where's the paper? Hold on, sorry. Oh, here it is. We started off with this equation, right? Let me zoom in with you. We started off with this equation, the e negative x sine x dx. We started off with this equation, correct? Well, that actually is this equation rearranged, and this is the original integral that we're trying to find. So if you rearrange this, you can get, sine x times you can get the integral of sine x times e to the negative x dx to be, you can take the negative out, negative to the integral of e negative x sine x dx. This is the equation that we started off with. This is the equation, this is the integral that we're trying to find. And from here, we can solve this integral algebraically by adding like terms. So this is the equation we originally were trying to find. This is the answer to that we're trying to find. We're trying to find the answer to this. But this also matches the second part of the second iteration. Remember, this is the answer from the second, this is the entire answer from the second iteration. This is the drop down of the uv, then minus the v du. But when we did the v du the second time, we still got this. And I rearranged it to make it look like this, which is the original, integral that we were looking for in the first place. This right here matches this right here. They're both, let me follow along. They're both the integral of e to the negative x times sine x dx. They're both equal. The two things underlined in orange are the same equations, which is the integral of e to the negative x times sine x dx. So let's solve this algebraically, and let's substitute the integral of e to the negative x times sine x dx. This was a little something I put out in whiteout, so just ignore this. This isn't a negative sign. It looks a little faded, but ignore that. But let's substitute the integral of e to the negative x sine x dx for the variable a. All right, so the integral of e to the negative x times sine x dx, which is what we originally have been trying to solve, is equal to, and this is from the second iteration, the whole shebang from the second iteration, e to the negative x times negative cosine x minus e to the negative x times sine x minus negative the integral of e to the negative x times sine x times dx. Note that these two are equal. This is the same thing, and we're going to make these two equivalent to a and solve this algebraically from this moment on. So a is equal to e to the negative x times cosine of x minus e to the negative x sine of x minus negative a. A little tip here, we're going to be adding something to both sides. And I know that if I add these two and I add these two and I plus it, then that would mean I would have to subtract from both sides, and a minus a is 0. So we can't do nothing with 0. We're trying to solve. We got to keep a. So I kept it as minus negative. If you come across a situation where the iterations keep repeating and the situations keep repeating, when you do the substitution, you have to get the signs such that if you either add or subtract, you won't end up with 0 for a. You have to keep this because this is what we're trying to solve. So if you come across this and you realize that if you either add to both sides or subtract to both sides or what have you, and you're going to get 0, either a, you have to go back and check your work because you did the signs wrong, or maybe you forgot to distribute a sign somewhere, or b, just try to tweak it such that you can subtract it, but it's still equal. Don't change the equation completely, but just make sure that it's you tweak it. For example, I tweaked it such that these two negatives could be a positive, but I kept it as two negatives because I want to add this to this side, and then when I add it to this side and subtract it from here, it'll just be sine x minus 0, and something minus 0 is just that same thing. You know what I'm saying? So yeah, just something to keep in mind. But anyway, a is equal to all of this, and we're trying to get a by itself because this is what we're trying to solve. That's the goal here. So we're going to add a on both sides. This negative a, we're going to add a here. This is a, not a 9. I'm sorry if the tail of the a is too long that it looks like a 9, but this is an a. So plus a, and then when you add plus a, this is just going to go away. So it's really going to be sine x minus nothing, or sine x minus 0. So we're just going to keep it as sine x. So yeah, it's just going to be this. So when you add a to both sides, this a goes away, but you add like terms here. This a plus a, you can think of it as 1a plus 1a, because anything times 1 is itself. So 1a plus 1a, or a plus a, if you will, when you add like terms, is 2a. So 2a is now equal to this right here. Now I rearranged this when I brought this down just to, like I said, brush it up or make it look pretty, which basically just kind of like distributes the negative, and I just put this over here. It doesn't really matter. All I did was like switch it, but you know, it equals the same thing. And I put negative cosine x to the negative cosine x times e to the negative x, which is the same thing here. Is negative cosine x times e to the negative x. I just put the negative here and put it here, and then minus e to the negative x sine x. So yeah. Now 2a is equal to negative cosine x times e to the power of negative x minus e to the power of negative x sine x. We have this, and we're trying to get a alone. So now let's solve for a. We got to solve for a, so we're going to divide 2 on both sides. Divide 2 on both sides. That's what we have to do to get a by itself. So since we divided 2 on both sides, we got a alone, which is equal to negative cosine x times e to the negative x minus e to the negative x times sine x divided by 2. That's what we got when we divided by 2 on both sides. This was 2a over 2, and the 2 is crossed out, so we just got a by itself. That's what we're aiming for. We got a by itself. And on the other side, when we divided by 2, we got negative cosine x times e to the negative x minus e to the negative x sine x over 2. So this is a, this is what a equals, and that's the goal. We're trying to get a by itself. Now we substitute back the integral for a, because remember a equals that integral that we were trying to solve. So now that we have a, we can substitute a for the integral. And the integral of e to the negative x sine x dx is equal to this. Negative cosine x times e to the negative x minus e to the negative x sine x divided by 2. That's what we solved for a. So now this is the answer to this equation. We answered it algebraically. The answer to this integral is right here. So this is the total answer, and don't forget to add plus c at the end. So then we add plus c at the end of the equation, and you have your answer. That's the answer right here. So the answer to the integral of e to the negative x sine x dx would be, once again, negative cosine x times e to the negative x minus e to the negative x sine x all over 2 plus c. So that's the answer, and that's how you would solve a problem that has multiple, that is going to have like multiple iterations with integration by parts. There you go. All right, so that pretty much concludes today's video, and that's all I have for my tutorial for integration by parts. I hope you guys enjoyed the video. Feel free to leave comments, questions, concerns, and I'll get back to you guys as much as you can. Feel free to let me know if there's any suggestions you guys may have about like the video, or like anything I could improve on to like help the learning experience for you guys as well. And yeah, once again, thank you for tuning in so much. Don't forget to like and subscribe, and I will see you in the next 2 weeks with another tutorial. Bye.